In today's lesson, we are going to talk about how to solve transportation problems. But before that, a little background about transportation theory. In mathematics and economics, transportation theory is a name given to the study of optimal transportation and allocation of resources. The problem was formalized by the French mathematician Gaspard Monge in 1781. Major advances were made in the field during World War II by Soviet mathematician and economist Leonid Kontorovich. Consequently, the problem as it is stated now is sometimes known as the Monge-Kontorovich transportation problem. The linear programming formulation of the transportation problem is also known as the Hitchcock-Koopmans transportation problem. So here is now our problem for today. A company manufactures a type of product in 3 different production plants. And let's call those production plants as P1, P2, and P3. The company supplies 3 customers, C1, C2, and C3, who require 65, 42, and 43 units per month, respectively. The unit transportation costs from each production plant to each customer are displayed in the table. For example, here, the transportation cost for transporting the product from production plant number 1 to customer number 1 is $5. The cost of transporting goods from production facility number 2 to customer number 1 is $4, and so on and so forth. Our goal in this problem is to optimize the transportation cost. Now, about transportation problem, there could be 2 types of transportation problems. One is called balanced transportation problem, and the second one is called as unbalanced transportation problems. For the balanced transportation problems, if you add all the supplies and all the demands, there should be equal amount or balanced number. And as the name suggests, when the supply and the demand total are not equal, then we have an unbalanced transportation problem. Now, in solving transportation problems, we are going to follow these steps. The first step is we are going to find a basic feasible solution using any of these 3 methods. Either we use the least cost method, or the northwest corner rule method, or the Vogel's approximation method, also known as penalty method. The goal of step number 1 is just to allocate the goods to each of the customers so that later on in step number 2, we are going to perform what we call as the optimality test in order to assess if our feasible solution is the one that will give us the least cost. Let me explain this using an example. In this problem, we are going to use the least cost method in order to allocate the supply to the demand. In the least cost method, the first thing that we're going to do is inspect the unit cost of moving goods from one facility to one destination. For example here, among the costs, this number 4 and this other number 4 are the 2 lowest costs. Since there are 2 of them, we can just randomly select any of these 2 values. Let's say we're going to select this first value. So we are in row number 2, column number 1. We want to allocate first to the cell because the cost of transporting goods here is the lowest. So we want to maximize the amount of goods that we can allocate to destination C1. If you go down below, we have a total demand of 65. And if we go to the right, we have a total supply of 50 units. So what we can do is select whichever is the smallest value. In this case, 30 is smaller than 65. So we can allocate all these 30 items to this cell. That means that we already used up all the available supply from plant number 2. And so we can no longer allocate for this cell, and we can no longer allocate for this cell. But since there's a demand of 65 and we just fulfilled 30, we still have to fulfill 35 more items for customer number 1. For the next step, again, we are going to inspect the cost and look for the cell with the least amount of cost. In this case, 5 is the lowest among 5, 7, 8, 6, 7, and 7. So again, we look at this 35 and we look at this 70. Which one is the lowest? The lowest is 35, so we can now allocate the entire 35 here. And therefore, customer 1's demand is already met. We do not need this part anymore. But since we already used up 35 here, there's still a balance here of 35. Because 70 minus 35 is 35. Then among the available cells, let's look at again the costs. The transportation cost here is 7, 7, 7, and 8. There are 3 7s. We just pick any one of them. Let's pick this 7. And then you look at this 42 and you look at that 35. The lowest is 35. So we can allocate the entire 35 here. And therefore, there's nothing more to allocate for the goods from production number 1 because we already have 35 and 35 to get 70. And since there's a demand here of 42 and we only fulfilled 35 of these orders, then there's still a remaining 7 unfulfilled items. And for the remaining 2 cells, both of them are 7. So we can now allocate this 7 here. And by allocating 7, we subtract 7 from 50 to get 43. And this 43 is now allocated to this last vacant cell. So that means our basic feasible solution as of this first step is from production 1, allocate 35 of the 70 to customer number 1, and allocate the remaining 35 to customer number 2. From plant number 2, we supply the entire 30 items to customer number 1, and for plant number 3, we allocate 7 items to customer number 2, and the remaining 43 to customer number 3. In this case, all the demands were fulfilled and all the supplies are allocated. So here is now the summary of what we just did, and we now call this as our basic feasible solution. And those occupied cells we call as our basic variables, and the unoccupied cells we call as the non-basic variables. Now we want to know how much is the cost now of this assignment. So for the total cost, we have 35 items here times 5, and we have 30 items here times 4, and we have 35 times 7, and we have 7 times 7, and we have 43 times 7, and this gives us a total of $890 for the transportation cost. Now, we do not know if this is the optimal solution. In other words, we do not know if we can still find a lower cost by rearranging this initial allocation. So we now move to the next step, which is the optimality test. For the optimality test, we call our rows are the use variable, and we call the columns as our vis variables. We start by assigning 0 for u sub 1. And then for this 5, we look at this 5 as the sum of this u sub 1 and v sub 1. And so we now form this equation, u sub 1 plus v sub 1 is equal to 5, which is this 5. And knowing that u sub 1 is 0, that means that v sub 1 must be 5. So we assign a value here of 5. We are going to use these values when we compute for the optimality test. Then, to find u sub 2, we know that v sub 1 is 5, and u sub 2 plus 5 is equal to 4. That means the value of u sub 2 must be negative 1, because u sub 2 plus 5 is equal to 4, which implies that u sub 2 is negative 1. Then for the next cell, we have u sub 1 plus v sub 2 is equal to 7. And since u sub 1 is 0, that implies that v sub 2 is equal to 7. So v sub 2 is equal to 7. By the way, u sub 2 here is negative 1. This is negative 1. Then let's compute for the remaining. You have u sub 3 and u sub 2. So this intersection here is equal to 7. And so u sub 3 plus the value of v sub 2, which is 7, that gives us a value of 0 for u sub 3. And lastly, for this occupied cell, we have u sub 3 plus v sub 3 equals this 7. And so, knowing that u sub 3 is 0, that means v sub 3 is equal to 7. So by using our occupied cells, we were able to assign these values for the rows and the columns, and we call them as our u's and v's that we are using in our transportation algorithm. Let's write this cleanly now in the next page. So we have these column values for V's and we have these row values for U. For the optimality test, for the non-basic variables, meaning the unoccupied cells, this is unoccupied, another unoccupied, and all of these marked cells are unoccupied. We are going to compute the weights for the cell. And the notation we use is Wij, where I and J are our indices to identify the location in terms of row and column. For example, this vacant cell here is at the first row, third column, so we will call this cell as W, first row, third column. And we are going to compute the weight using this formula, U sub I plus V sub j minus C sub ij. And if the results that we get here for each of these non-basic variables are all less than or equal to 0, that means the table is in the optimal solution. If there are positive values that we arrive at, we're going to use loop pivoting in order to tweak and improve our allocation. So let's compute first the weights. So for this empty cell that is at row number 1, column number 3, we are going to use U sub 1 and add that to V sub 3. So you have 0 plus 7, which are these values, 0 and 7, and subtract the cost in that empty cell. The cost is $8, and this gives us a cost weight of -1. And we are going to do that for the remaining 3 other vacant cells. So for the second row, second column, we got +1. For second row, third column, we got 0. And for third row, first column, we got a cost weight of -8. Notice that all these 3 are optimal except this +1. And that +1 happens at this cell. In order for us to see where are the locations of all these weights, let's put those values in the cells. So this is negative, this is positive, this is negative, this is 0. So we are only concerned about this positive because all the rest are already in their optimal state. Once we identified which one is the positive value, if there are several positive values, you start with the highest value. In our case, there's only one positive, so we are only concerned with the cell. Now, in this case, we are going to form this loop. Either the loop goes counterclockwise or clockwise direction. But the way to identify the direction of the loop is from the empty cell, you look at the 2 adjacent cells and you count it like this: 0, 1, 2, 3, 0, 1, 2, 3. For all the odd cells, we are going to subtract, and for all the even cells, we are going to add. So this is 0, 1, 2, 3. That means we are going to subtract here, we are going to subtract here, but we are going to add in this even number of cells. You look at 30 and 35, the lower value is 30. You pick that lower value 30, and you add that to this empty cell. So subtract 30 here, but add the 30 here. So you now have 30 added in the cell. But in order to maintain the balance, since we are adding more supply to this customer number 2, we need to subtract 30 from this 35 so that customer number 2 still get what it orders. We do not want to oversupply customer number 2. So we are going to subtract 30 here. And by subtracting 30 here, you are removing some of the items for plant number 1. So you are going to transfer that by adding whatever is subtracted here. So plus 30. And since this one was already transferred to the other side, this must be empty. So this is now how this would look like. We transfer the 30 from here going here. We subtract 30 here, and therefore we have 5. And then the 30 that we subtracted in this cell, we added to the left to get 65 here. And we now have a new allocation. We just reallocated the item from here going to this part, which was initially vacant, and we perform this pivot, and we complete the loop. That's why we call this as the loop pivoting. Now, after performing this loop pivoting, we would like to update our weight. So we want to find the weight of row number 2 and column number 1. And the weight now is computed as -1 plus 5 minus the cost here of 4. And -1 plus 5 minus 4 is equal to 0. That means we now arrive at an optimal solution because all our weights are -1, 0, 0, and -8. All of them pass the optimality test. That says the weights as computed here must be less than or equal to 0. So in this new allocation, let's compute how much is the transportation cost. So here is now the total cost. We have 65 times 5, and we have 5 times 7, and we have 30 times 4, and we have 7 times 7, and we have 43 times 7. And this gives us a total of $830. Notice that initially, our total cost was $890. By performing this loop pivoting method and making sure that the result passes the optimality test, we arrive at a minimum transportation cost of $830. So this is one method of solving transportation problems. In the world of Amazon and other delivery companies, the problem is more complex, but with the use of fast computers and using these algorithms, these companies are able to maximize their resources, minimize the time and the cost of transporting goods from production facilities to household customers. And much of the development of these algorithms happened during World War II, when the demand for transporting soldiers and resources and foods and other supplies challenged different governments to do it fast, using the least amount of resources and time in order to win World War II. So thank